Our first chain rule suggests another chain rule almost immediately. So assume that g now is a function of a parameter vector. So instead of one parameter, we have, say, s parameters. And it's actually the composite of a f u of t, where u is from rs into rn, f is from rn into r1, and therefore g is from rs into r1. Well, if we fix all of the parameters, all but one parameter, and allow one parameter to vary in this parameter vector, then we have restricted the function so it's of one parameter into one-dimensional space. And that allows us to apply the chain rule, our first chain rule. Well, when we do that, that tells us exactly what the partial derivative is, right? If we keep everything fixed and we vary one other thing, we can calculate a partial derivative. So that suggests exactly this form for the partial derivative with respect to the ith variable. So our second chain rule is dg dti for all I at a particular t, and this exists when all these other quantities exist and are nice. df of x1, so that's with respect to the first parameter of x1. I'm going to evaluate it at u of t. But now here's what's funny. Now instead of x1, my coordinate function here is u1, and it takes in a parameter t, and I'm only varying the t ith parameter, so I multiply this is not a dot product, I multiply it by the scalar quantity du1 dt I of t, plus the next term is going to be df dx2, derivative of f with respect to the second coordinate. It'll still take u of t as its argument, and I multiply, not dot product, these are both scalar quantities, du2 now of dxi of the parameter vector, plus, keep going down the line, up to the nth coordinate, dxn of u of t times du n of, sorry, this should be a ti there, not xi, dti of t. And that's our second chain rule. Again, this is it's just a bunch of symbols, and so we want to actually do some computing with this thing. So let's get an example on the board. Consider standard production function, Cobb-Douglas type, KL is equal to 4k to the 3/4, and L is 1/4. Good. But now our capital and labor are going to be functions of time and interest. K of tr, and these are our parameters, is equal to, say, 10 t squared. So over time, my capital is increasing by the square of the time, so it's increasing really quickly, and I divide by the rate. So if the rate is small, that means that my capital is increasing more rapidly. L of tr is equal to 6t squared, so it's increasing like that with t, but I've got a proportional relationship with r now. Now I have to, in order to examine this, I want to know, well, how is this production changing over time if these are my functions? So my partial derivative, dq dt of, and this will be of k of tr and l, but let's ignore that for now because it's a lot of writing. And oftentimes we'll suppress the arguments just so that we don't have to waste a whole lot of space, because you'll notice that if we write all this out, it looks actually really much more confusing than if we just write out simple partials. So this is dk dt plus dq dl times dl dt. Well, if we compute all those things, and these are nice monomial term like objects. They're, these are to the 3/4, but we just have to deal with exponents. We're going to get 3 k to the negative 1/4 L to the 1/4. So these are still functions of t and r, but I've just suppressed the argument so that I don't have to deal with it. 2t, still r inverse, plus k to the 3/4 L to the negative 1/4. Again, suppressing arguments. 12t. So if I take partial of this guy with respect to t, I kill the r term. And now let's fix a particular set of numbers so we can actually plug it in to calculate. Well, we've got t is equal to 10, r is equal to, say, 0.1. Therefore, k of 10, 0.1 will be 10,000. We'll have that L of 10, 0.1 is equal to 625. And we plug all these things in to that expression, and we'll get 3 times 10,000 to the negative 1/4, 625 to the 1/4, times 20 times 10 times 10, because we invert the r, plus another term here is going to be, the next term is 10,000 to the 3/4 now, 625 to the negative 3/4, times 12 times 10. And we get 3,960. So our production at that instantaneous moment is increasing by 3,960 units. And that can be a very useful piece of information that we have a nice tight formula for calculating.